Hello, everyone, and welcome to our second on-site meeting at PACE. Our speaker is Professor Frederick Walter, a longtime faculty member from the astronomy department at Stony Brook University. Fred holds an S.B. in physics from MIT and a Ph.D. in astronomy from the University of California. Being an observational astronomer, it has brought him the opportunity to work with observatories based in Arizona, Chile, and Hawaii. In addition, the Hubble Space Telescope and the X-ray telescopes of Cassandra and XM Newton. Professor Walter's research has been in understanding the dynamics of young star formation. His lecture will focus on the variability of Tauri stars, first discovered in the constellation of Taurus. I am confident that you will come away with a new perspective the next time you observe Taurus in the night sky. Please give a very warm welcome to Professor Walter and his wife, Paulette. Thank you.
Thanks, everybody. Nice to be here. This is the second live performance I've done in the last 2 years. Faculty are expected to perform, so that's why I call it that. Do I have to stand right by the mic?
I can walk around a bit.
I can, okay, that's good. I want to talk to you about one of the projects I worked on, which is variability of Tauri stars. And I'll tell you, try to teach you a little bit of stellar physics, if you, whether or not you want to. Learn it, I will tell it to you anyways. The background picture here is a star-forming region. This is not in Taurus, this is in the constellation Corona Australis. Most of you have probably never seen. It's minus 40 degrees declination. Star-forming regions are marked by dust and gas clouds. That's what stars are formed from. We're going to talk about not the initial formation of stars, but what happens to them on the way to becoming something like our sun. Now, how do I advance the slides?
Oh, you can just use stuff.
Oh, okay. All right, thank you. Good. So let me start off by saying that all stars are variable. All stars. This is a plot showing you the total solar irradiance. This is the brightness of the sun as a function of time going back to 1977 or 78 for solar cycles. And the sun varies, but not by a lot. 0.04% is the mean variation. The red daily measurements of the total solar irradiance. The green is smooth over. Smooth over.
Could we everybody mute on Zoom, please?
Oh, sorry.
And those big drops at the bottom, falling down. Does the cursor show up here? Yeah. These big drops like this one are due to sunspots crossing the surface of the sun. Keep that in mind when we talk about the variability of Tauri stars. They lead to about 0.2% drops in the brightness of the sun for a few days. But overall, the sun is brightest when it's most spotted. But the sun varies. Keep this number in mind by less than 0.1%, 0.04%. So we're not going to talk about the sun, as fascinating as it is. We're going to talk about Tauri stars. They were identified as a class of stars back in 1945 by Alfred Joy. They've been called the stars of joy by some, but not by me. The characteristics of the Tauri stars, which comes directly from Joy's paper, is that they are irregular variables by up to 3 magnitudes. 3 magnitudes is about a factor of 15 in brightness. not 0.04%, a factor of 15. Otherwise, they sort of look like the sun. They have spectral types, G0, give or take. They're low luminosity, that means a solar luminosity, give or take. And they're always associated with nebulosity, dark clouds, or bright nebulosities. George Herbig further studied them and defined them in 1962. And he told us about a lot of them. Okay, so what are they? They are low mass, pre-main sequence stars. Low mass meaning about the mass of the sun or less. They're going to turn into stars like the sun, G stars, K stars. They have masses less than about 2 solar masses. Higher mass stars or do something different. They're young. They have ages less than about 10 million years. I'm not going to tell you how we know they're young, except they're accreting matter. They're not at their final masses. They're building up mass by accretion through a disk. And we get disks are ubiquitous in astrophysics because of conservation of angular momentum. When if you have a spherical cloud that's rotating and it collapses, it will collapse along the axis of rotation, and you end up with a pancake. And then the stuff will come in through the disk because of friction. We call it viscosity, but it's friction. The prototype, of course, is Tauri itself. And there are a few nearby star-forming regions listed here. If you ever want to go up and look out at the night sky and say, where are the stellar nurseries? Taurus, Auriga has one. The belt of Orion is a nursery of young stars. The whole Scorpius Centaurus Lupus Association has lots and lots of young low mass stars. There's one in Chameleon, even further south at -70 degrees, and Corona Australis. The image here is a painting by William Hartmann that shows an outer's conception of a young sun or a young pre-main sequence star shining through its disk of material. This material, these rocks, these asteroids, this dust will eventually build up into planets. So we use the term circumstellar disk and protoplanetary disk more or less interchangeable. They're very intimately related to what the Tauri stars do and why they do it. So this is a picture of what we think a Tauri star looks like. There's a lot going on here. There's a star. Up here on the left, you can see a star. And the star is not uniform brightness like the sun sort of is. It's got big spots on it. You see that big gray thing at the top? That's a polar spot. It's covering 10%, 20% of the star. Oh, thank you. Okay, so here's a star, a giant star spot. We know that young, rapidly rotating stars tend to have spots near their poles, not near their equator. These blue bands surrounding the equator are where matter is falling onto the star. Where's that coming from? Here's the disk, the circumstellar or protoplanetary disk. It's moving in with time. It gets in here and it gets entrained in a magnetic field. This is a rapidly rotating star. It's got a large magnetic field compared to what the sun has. It's more or less dipolar in character. Hence these loops like this. And this is where this standoff region is with the magnetic pressure equals the ram pressure, the gas flowing in. The gas is slightly ionized. It latches onto the magnetic field lines, and it comes in and lands not on the equator, but at high latitude. It's sort of like the terrestrial aurora. The solar protons come in and latch on a field lines and come down and give you the auroral arc at high latitude. So you have the stuff falling onto the star that releases energy, gives you ultraviolet radiation. You get X-rays from hot gas trapped in here, and you see dust emission out here. So you don't have just a simple star like the sun. You have X-ray emission coming from circumstellar regions, ultraviolet light, you have stuff getting in the way, dust blocking light, depending on the angle you look at. They're very complicated. We've built up this picture since 1945 because we've been trying to explain why do they do what they do? How do we explain the variability that we see? Here's a picture of a young star, a three-main sequence star. You don't see the star. You're looking exactly in its equatorial plane. It has a name. It's called Gomez's hamburger. A Mexican astronomer named Gomez published this picture. This is the edge-on circumstellar protoplanetary disk. The star is in here. And what you see up here is scattered or reflected sunlight from, well, dust above and below the plane. Stellar light is reflecting off it and coming towards you. So we're looking edge on at a protoplanetary disk here. Here's a baby picture in the, tell me if I get too far away from the microphone, from the in the Orion Nebula. There are lots of young stars in here. These are images from the Hubble Space Telescope showing some of the different characteristics. Look, here's another edge-on one. Here's one where you see the disk more or less face on. This is sort of weird, but there's a shock wave. This stuff is blowing out from the star. Here you see what looks like a jet from the star and a black disk, a black hole around the star. These are all young stars, 1 million years old, give or take, surrounded by disks of material, flattened disks, and they have jets coming out the poles too. So they're complicated. This is a blow up of one of those regions showing you a face-on disk. That is a reddish dot right there in the middle. That's the star. It looks more or less circular. How it's face-on. How big is that? It's about 100 astronomical units in radius. That's about the size of our solar system. Pluto is 40 astronomical units out. So this is a solar system being born. This is a bright nebulosity. There's a star buried in there. It's being heated up. This is the Orion Nebula in the background. So this may actually be illuminated by the O stars in the Orion trapezium. But there's another disk here and a disk there as well. So these are all over the place. If you know where to look for them, how to look for them, if you have access to the Hubble Space Telescope, you can find them. Is a slightly more complicated region. This is in Taurus. This is a star called HL Tauri, which is buried in here. There's an occulting disk blocking the light from the star, much like the occulting bar in the SOHO image of the sun you saw earlier tonight. Another T Tauri star here. And what you see is there's some evidence for like a jet coming out in this direction. Lots of gas and dust surrounding this. And this is what the star itself, right in here, looks like when you look at it with the ALMA radio telescope, sub-millimeter telescope. It's sensitive to warm dust. This is the disk. And it looks like a record, a long playing record. Those of you my age know what an LP is. Some of you may not. But these rings, the dark bands in here are either places that have been cleared out by a planet forming in the disk, or they're just shadowed because the disk is not smooth, it's irregular, and it could be there's a bright ridge in here and it just shadows the stuff down here. We don't really know. It's hard to see the planet, but there's a lot of structure. And that leads to the amazing variability of the T Tauri star. So just to sort of recap this, the variability comes from the types of variability we see and we're looking for is there are dark spots, mostly towards the poles, but not always. There are bright regions, bright hot spots due to the accretion. They're drawn as bands here, but they're probably not uniform bands. They're probably discrete hotspots. I'll tell you, they are discrete hotspots because I've observed some of them. If you're looking at a low angle, you're obscured by the disk, and the disk is not smooth. So you can have variable obscuration of the star by an irregular disk. You can have obscuration by the stuff in these field lines when the ionized gas gets trapped in the field lines and falls into the star. It carries with it dust and neutral gas too. So there is variable obscuration. If one of these crosses your line of sight, you can see it, and I'll show you an example of that. And you've got what's not shown on here is you've got stellar wind. Well, it is. Here's a stellar wind, a disk wind blowing off the disk just because it's heated up and it's moving faster than the escape velocity. There's also winds coming out of the star too that are not shown here, and they get in the way sometimes, and you can see them. So there's a lot going on here. Here's an example, real data from a star called T-Chart. The data are from the Assassin project. They monitor the whole sky every few nights, looking for variable objects. They're looking for supernovae. That's what the SN means in there. But this star, you can see, look at the scale. 10th magnitude down to 14th magnitude, four magnitudes. It's about a factor of 40 in brightness. And the star is going from nearly 10th magnitude down to 14th magnitude. It's varying by a lot. The time scale here, this is about 3 years, 4 years, and it's going. And from data like this, all you can say is, boy, this is variable. There's not enough data, not a high enough cadence to really give you a good picture. But we do know one thing about this star. We're not looking at it face on, we're looking at it nearly edge on. We're looking right over the top of the disk. So we're seeing partial obscuration of the star from the disk. I'll show you a little bit more of that later. It's one of the most variable of the Tauri stars. In this case, this is another artist's conception of what a Tauri star looks like. In this case, we're looking actually on a line of sight, more or less like this. And this disk is not flat, it's actually corrugated. So you're blocking light as the disk rotates. Okay, so an aside before I start wowing you with data, what are the instruments we're dealing with here? I'm going to show you some spectroscopy. This is what I do. I use a telescope, 1.5 meter telescope in Chile. It's the SMART Sartololo 1.5 meter, used to be the 60-inch. It's a fiber-fed shell. I will show you some photometry taken from the ground, a lot from the AAVSO. Are any of you members of the AAVSO? Okay.
We have one from who's on the Zoom, at least one.
If any of you want to get serious about taking data, they're a great resource. Finally, and I'll tell you about the TESS satellite, the Transiting Extrasolar Satellite. Have you heard about that in any of your talks? Good, I'll wire you with that too. It's a space-based photometer, and because you're above the clouds, and you can look at things continuously at high cadence for long periods of time. It basically works at red light, and you get an image, well, right now every 10 minutes for 27 days. Continuously. That's a lot of data. That's better than one observation every 2 or 3 nights. It's more confusing too sometimes. So this is the telescope I use in Chile. This is the 1.5 meter dome. At sunset, you can see the Andes in the background. The telescope itself, here are 2 shots of it. It's an old telescope, was built in the 1960s. It's a basic cast-screen telescope. Looking up, there's the telescope on it. In case they lose pointing, it's still possible to figure out where you are the old-fashioned way. The instrument is a bench-mounted shell spectrograph. The way this works is the light comes in here. The light, it goes from the primary mirror on the telescope to the secondary mirror to the hole in the back of the primary mirror, the cast screen focus. it goes into a fiber. That fiber then goes down the pier of the telescope into a room underneath the telescope, and it exits the fiber here, gets re-imaged. I don't use the iodine cell. That gives you precise radial velocities, which you need for finding planets, looking at small velocity shifts in stars. And then it's a mirror, it goes out to a collimator, goes to the shell grating, goes to cross disperser, so you can get into a two-dimensional spectrum. I'll show you what it looks like, and it gets sent into your CCD camera. This is the picture. It's actually all enclosed in a dewar. It's kept cold, and it's kept in a vacuum. But the light comes in here, and it goes to here, and it goes to here, and it goes to the prism, and it comes to the folding mirror, and goes to the CCD camera over there. I've never seen it. It's in the enclosure. You're not supposed to look at it. It's very stable. They don't want anybody playing around with it. And this is what you get at the end. It's a this is an image 4096 by 4096. It's 2 CCDs showing what a two-dimensional spectrum looks like. The wavelength increases from, this is the blue end to the red end, and it increases blue end to the red end here. The shell splits it going in this direction at very high resolution, and the prism splits it this way, fairly low resolution. So we get in a very compact format, you can get an awful lot of spectrum, from about 4,000 to 9,000 actions, essentially the entire optical band. Things you might recognize in here, this is atmospheric telluric oxygen, the Fraunhofer B band. There's actually an emission line right here, but it's hard to tell when it's black and white. And there are instrumental artifacts we know all about. Any dot on there is a cosmic ray. So this is the data I work with. The idea, what you do is you trace this and you put it into a one-dimensional format, and then you can look at it. If you've never been to a medium-sized telescope and run it yourself, this is what the 1.5 meter control room looks like. This telescope used to be run by 3 or 4 people. Now it's run by just the observer. So the control room is much, much bigger than it needs to be. And then you sit over here where you monitor all these screens. You have, it keeps you awake. There's a screen that tells you what the telescope, where the telescope is pointing, and this is where you tell it to move. This is the instrument control, which is rather complicated. And this basically tells you what the weather is outside, because you don't have the time to go outside and look at how clear the sky is. Actually, you do once you get the observation going, because the telescope tracks very nicely. TESS, the Transiting Exoplanet Survey satellite, has been up for nearly 4 years now. It images a very large part of the sky, 24 degrees wide by 96 degrees. About 27 days, then it goes around, because it has to follow the sun. That's about 5.5% of the sky being observed at any one time. And the first couple of years, they sent out an image every 30 minutes. They figured they could do better. They now do it every 10 minutes. And starting next year, you're going to get an image of the sky every 200 seconds, every 3 1/3 minutes. Lots of data. So the way this works is in 1 year, you basically do one ecliptic hemisphere. They started in the southern hemisphere, then the northern hemisphere, then they did a swath sort of line ecliptic, and they repeated the north and south. You want to observe, they avoid the ecliptic plane because planets are bright. You want to avoid bright things, especially the moon. This is what it looks like pre-launch. Solar panels here and here, cameras up here. Basically very small telescopes. There's a star tracker up there. This is the observing layout. This is 4 CCD cameras, each covering 24 by 24 degrees on the sky. It tiles the sky here, then it goes here, then it goes here. So in the year, 13 by 27 days, basically, you have really good coverage at ecliptic pole, then very good coverage down to about 20 degrees ecliptic latitude and sparse as you go further down. And it's just designed to look for transiting exoplanets. It gets basically every star in the sky down to 17 magnitude, and if they have a Jupiter in a close orbit, it's going to find it. All the hot Jupiters in the sky. The instrumentation, these cameras, they're big cameras, 17 megapixels. The telescopes are 2.5-inch telephoto lenses. They're small, but you're above the atmosphere. You've got very sensitive detectors. You can still see down to 17 magnitude. The only drawback is that the image quality is pretty poor. The pixel size is 21 arc seconds. And what does that mean? Well, on the right is a picture of the sky, and I don't remember which field this is. And on the left is basically the same field observed in tests. Can you see the similarities? These three stars are this one, and this one. That is this. You'll see there's a couple of stars there. You can't tell from that. So the image quality leaves a lot to be desired. But that's not what the purpose of this is. It's doing photometry, high cadence, high fidelity photometry on brightish stars. Now, I thought I'd educate you a little bit on variable stars. Why is T Tauri called T Tauri? Do any of you know this? Did you take Astronomy 101? Forget it?
Because that's where it was first discovered.
But what's the T? Why is it called T? Tauri is a constellation. That's true. So, for some reason, astronomy rests a lot on tradition, and we don't know where many of these traditions came from. But the first variable star in a constellation got the name R. And the next one discovered became S of that constellation. Then T is the third variable star cataloged in that constellation. This comes after the bright stars getting their Bayer, alpha so-and-so, beta so-and-so. These are Roman letters for the variable stars. So T Tauri was the third variable star cataloged in the constellation Taurus. It didn't take long before they started running out of names. Once you get to Z, where do you go? A was already being used for various things. It's not like P Cygni. P does not fit in this categorization. So they said, well, let's double up. Next one is RR, RS, RT, on down to RZ. Then you start over with SS, down to SZ, TT, down to TZ, all the way down to ZZ. Then what do you do? There are lots of variable stars in the sky. And you start over here with AA, AD, AC, on down to AZ. And eventually, once you get the, you run out of these combinations after 334 stars. Then somebody wised up and said, well, let's just put a V and then a number. So the 335th variable star discovered in the constellation is called V335, such and such. So that's how stars are named. It's a good thing they went to this numerical scheme because as of a year ago, I was working with a Nova Sagittarii 2021b, which has a variable star designation of V6595 Sagittarii. There are lots of variable stars out there, and if you look hard enough, every single star is variable. So that's where the names come from. So let's get into T Tauri and why it is what it is. This is an optical image of T Tauri. You can see this nebulosity here. It's called Heinz Nebula. It was discovered in the 19th century. Clearly a region that has dust and gas surrounding it. It was studied 20 years ago now by two astronomers at Stony Brook, Mike Simon and Tracy Beck. And they looked at the Harvard College Observatory plate stacks because it's not a wildly variable star now. And if you were to start categorizing or classifying stars as variable in Taurus, this is not one you would pick out. This is the light curve from 1917 to 1950 something. And there are a few glitches. It's very low right here and right here. But during these 20 years, it doesn't do much at all. Not really going to stick out. I mean, it's variable maybe as a 1/10 of a magnitude level, but that's not much. But if you go back in time from when the plate stacks begin, back in 1895 up to 1917, it is highly variable. It's going up and down by 3 magnitudes. That's a factor of 15. This is clearly a variable star. Something interesting happened to it in 1917, and it stopped varying, or at least it became very much less variable. We'll get back to this at the end of the talk. This is what you see when you look at Tauri with the test satellite. This is 27. This is 2 seconds. This is 54 days, and it's clearly not constant. It's a variable star, as you would expect. But the amplitude, these are instrumental magnitudes. I can add any arbitrary number to it. It's -2.5 times the log of the number of counts per second. So from here to here is 2/10 of a magnitude, 20%. T-cha is varying by 4 magnitudes. This is 2/10 of a magnitude. This is not very variable, but it's clearly variable. Is an overall downward trend. There are these dips. So it is a variable star. It's just not a wildly variable star right now. I'm more interested in the wildly variable stars. This is T-cha, again, the one I showed you the ground-based data of. This is 54 days worth of observations by the test satellite in the year 2019. And this is going up and down by 3 magnitudes, much like it did on that ground-based data. And you look at this and say, it's sort of a regularity here. Maybe there's a period. It's quasi-periodic. So it goes down and up and down and up and down and up. And this seems to be a high level, but lots of little levels. Okay. Why is it doing this? We've done, with a colleague of mine in Colorado, we've done some photometry on this, and it doesn't get red when it gets faint. It doesn't get blue when it gets bright, which is what you might expect if it was due to star spots or accretion heating making it bright. You're just blocking light from the star. Remember, this star is being observed right over the top of the disk. We're mapping out irregularities, corrugations at the top of the disk. And they're more or less periodic at a period of 3.5 days, which we think is half the rotation period of the star. The inner disk is magnetically connected to the star because the magnetic field is threading the inner disk. So the inner disk is rotating in 7 days as well. That's called the Keplerian co-rotation radius, where it's basically where a geosynchronous satellite would be. You're rotating at the same rate that the star is. So we're mapping out the irregularities and how they vary in the disk in the star. Tess looked at it again 2 years later. Found out about the same. The variations are about half as big, 1.5 magnitudes. But after a month, it stopped dipping. In fact, it looks like there's some nice little bump, positive excursions here. Very periodic, as a nice 7-day period, as we expected, 3.5-day period. So something happened to change the disk. We don't know quite what. We don't have good spectroscopic coverage of this, but we'll try to put together something that describes what it's doing. Just to remind you, you're looking at this angle. You're coming in right over the top of the disk. It's inclined 75 degrees, 90 degrees is Gomez's hamburger, where you're looking right down the middle of the disk, 50 or 15 degrees off, and you're looking at the bumps and wiggles in the top of the disk, physically obscuring the star. My contribution to this is the spectroscopy. These are four spectra of the H alpha line, bright line of hydrogen. These are not coincident with the test observations. They're up there just to show you the line varies. Different colors at different nights. These are the nights, Julian days, minus 202,460,000. And what you see is there's an absorption here. There's some absorption here on a couple of nights. But the whole thing varies quite a bit. The spectroscopy is changing. This is not just the brightness of the star. You're blocking where the hydrogen is emitting. And the hydrogen is not coming from the surface of the star. It's coming from a much larger volume. I'll go over this very quickly. We have to try to reconstruct what the hydrogen line profile would look like in the absence of the disk, in the absence of this variable obscuration. We never see the star without the disk in the way. So you sort of have to wait, pick out the bright points, the bright parts of the line and put them all together. So you say, okay, we have a spectrum in black and it's got this, it comes up like this. And we can say, well, that's what the star does when you're not obscuring it. It's very different on this side. It dips down. There's something blocking the light at those velocities. So we say, this is what the intrinsic line profile looks like. So you reflect it. You say the line is symmetric. That's the green coming down here, and you make it a Gaussian. So this green is what is our reconstructed line profile. And once you say this is what we think the star looks like in the light of hydrogen. This is velocity, brightness versus velocity. So this is stuff that's coming towards us at going away from us at 200 kilometers per second, and stuff coming towards us at 200 kilometers per second. And the star is rotating maybe 10 or 15 kilometers per second. So this is far away from the star. This is the magnetic funnels attached to the disk, which are rotating in the same period, but they're much further away. So they're coming around at a very high velocity, 10 times the stellar rotation or so. So we construct this and we can subtract that from every single line profile we get. And this is what happens. These are the differential line profiles. This is the spectrum we see minus that reconstructed line that we think is what's really underneath there. And there's no evidence that is changing. And what you're seeing is a few changes out here, some changes here. This is stuff falling in at high velocity to the star, 300 kilometers per second. That's free fall onto the star. This is stuff coming down a magnetic funnel just before it hits the star. And so you can map that out. It's not always there, but sometimes it's there. This is stuff that's only falling onto the star at 100 kilometers per second. So this is stuff that's not just about the crash into the star, it's further out. Or it's just starting to go in. So if we have a dense enough coverage here, we can map out where these magnetic funnels are and try to correlate them with the bumps and wiggles in the accretion disk itself. Accretion disk is the third synonym here: circumstellar disk, protoplanetary disk, and accretion disk. They all mean more or less the same thing. You've all heard about redshifts. Redshifts are big in cosmology. The universe is expanding. We talk about redshifts too. They work at low velocities. In Tauri stars, we see redshifts and blue shifts, but they're not of order unity. Now, everybody loves these distant galaxies with redshifts of 6. We're talking about things that are redshifts of 0.0003, almost nothing. That's 100 kilometers per second. So the redshifts, changes in velocity here, tell us whether the stuff is coming towards us or going away. This stuff is at plus 100 kilometers per second. It's moving away from us. It's an absorption. It's being blocked by stuff between us and the star, or it's actually physically occulting the photosphere of the star, but it's moving away from us. And just to remind you, you're again looking down here. So we're looking at gas here that is starting to fall in towards the star, or gas up here that is falling into the star. This is higher velocity. This is low velocity, and then gravitational free fall accelerates it as it falls in. So we can map where the gas is in these magnetic funnels. This is a star you've never heard of, CVSO 109. It's in the Sigma Orionis cluster. That's below the belt of Orion. It's the star with the blue plus on it. This is looked at by the Hubble Space Telescope and by TESS, and we got some supporting ground-based observations too. And this is a whole bunch of photometry. This is mostly from the AAVSO. It shows the changing colors. This is the TESS light curve, and the red line is when the Hubble Space Telescope looked at it. We're doing ultraviolet spectroscopy because that tells you something about the accretion. The accretion hotspots should be bright in the ultraviolet. You're releasing energy when you hit the star. So you'll see it was cleverly scheduled to happen at a peak in the light curve. The star brightened by 0.05 magnitudes, 5%. It's hard to tell what's going on from photometry alone, but it turns out the spectroscopy gives it away. This is brightness versus velocity. In white is one of 3 spectra that I got, and it's more or less symmetric. It goes pretty bright. So what I did, and I said that one in white is my reference spectrum, and I subtracted that off the other 2 spectra. So the first spectrum, which is called day -1 here, is in yellow, and the reference, there's a dip here at 200 kilometers per second. There's stuff flowing into the star that we see against the stellar photosphere and moving at a velocity of 200 kilometers per second. You can see it before you subtract the reference off, but clearer if you subtract the reference off. The next day, which coincides with the Hubble Space Telescope observation, when the star was brighter in TESS, the line is bigger. There's a lot more flux in the purple line than in the red line, and this has gone away. That absorption has gone away. The third day, it's actually somewhat weaker, but everything has sort of settled down. There's a big tail off to the red here at high velocity. So our working hypothesis is that the day before the observations, we see a bunch of gas falling down onto the star. We see the absorption here at 200 kilometers per second. The day of the Hubble observation, when it got brighter in TESS, that blob of material falling down at 200 kilometers per second has hit the star. It's brightened up the star. It's heated up. By heating up the star, you brighten the emission in the hydrogen line. And by the next day, it's cooled off. The star gets brighter into photometry and TESS, and it's faded away the next day. So the ground-based spectroscopy lets us interpret what the photometry is doing. The Hubble Space Telescope spectra, we just have one. It's hard to interpret, but at least we have it in context now. The spectrum was taken when the star was brighter than normal because it had just suffered from an accretion event and brightened it up by 5% in the optical, probably by a lot more in the ultraviolet. Star called TW Hydri. We're looking at it face on. Tell me when I've started going too long, please. TW Hydri is a face-on, fairly active Tauri star. This is the ALMA image. This is the dust, the warm dust. It has, again, the phonograph record appearance. It's got rings in it. Could be planets forming. It could be shadows in the disk. We really don't know. If you look at high resolution in ALMA, this is the spatial resolution. This is 1 AU. This is the inner part of the disk, where it's about 1,500 degrees or so. You'd like to see a planet in there. We don't. It's hard to see planets. They're small and not particularly bright. But this is face on. It's inclined to the line of sight by less than 7 degrees. When you look for the ground, you see it's variable. It is indeed a Tauri star. It's variable. It's in a region of star formation. In the blue band, it goes up and down by a magnitude or so. In the V band, by almost a magnitude. This is amateur data from the AAVSO. This is the test light curve. The looks much more impressive than the AAVSO light curve. Mostly because high cadence. There is a point every 10 minutes here. No, this is every 30 minutes back here. Well, one or the other. And it doesn't stop. There's no night getting in the way. Okay, and it's pretty high signal to noise too. The green is when we got spectra, and you can see it's going up and down by 30 or 40%. It's variable. It's not the most variable star out there, but you cannot go to use the same mechanism we used to explain T-char, because T-char is edge on, this is face on. There shouldn't be anything blocking the light. But something is getting in the way here. So hopefully we haven't fully analyzed the spectra yet, but the spectra will tell us, now what's the difference in the state of the star between when it's bright and when it's faint. Here are spectra. There are 34, well, there's about 30 spectra here over 34 nights. And you can see that the line profile, this is now in wavelength and not in velocity. It changes. There are bumps and wiggles out here because in this case, it may be a wind from the disk getting between us and the line of sight to the star. There is absorption here at 50 kilometers per second. That stuff, that's the magnetic funnels falling down onto the star, somewhere near the magnetic poles. They're messy. It's not all in forming this nice little tight torus at plus 60 degrees. It's fuzzy. So there's stuff splashing around and even covering the pole. But you can see it's varying night to night, and we're trying to correlate that with the photometry and come up with a picture. This is weather on Tauri stars. We sort of know what it's doing, but this is mapping the day-to-day variation. We're looking for characteristic time scales, characteristic velocities, trying to figure out what the thing looks like. Here's another interesting follow-on system. It's called RU Loopy. One of the best names ever for a Tauri star or any variable star. This is also almost pole-on, but this varies by more than Tauri. I don't have spectroscopy simultaneous with this, with the test observations. We're going to try to do this again in a year. But you can see this is varying by nearly a magnitude, about a factor of 2 or so. And that's hard to explain. If you can explain TW Hydri, 40%, this star, factor of 2, it gets harder to explain. And the H alpha line does change. This is a different epoch, different set of data, different times. But here you see some mass loss at 250 kilometers per second, mass loss at 100 kilometers per second. This line is very broad. The whole star is brightening on the red side, so that stuff falling into the star. And at the top of the line, lots of variation. This is stuff at velocities of about 50 to 100 kilometers per second. These are the accretion funnels flowing down onto the star. We can map out the mass accretion onto the star. Briefly, some other examples. As stars start to lose their disks as they get older. They become a little bit less chaotic, less variable perhaps than the young the pre-1917 Tauri or Cha. This is GMRIG. Now we've got one in the Northern Hemisphere you guys can go out and see. And it's varying by 5%, sort of chaotically. But it's got this thing that looks like flare. Well, it's not a magnetic flare because they have a different profile. I'll show you some magnetic flares in a few minutes. But this is a brightening. It's quite obvious. We have some spectra during that time. I don't know what. No, this one I do not have spectra during that time because it's hard to get GMRIG from Saratololo. Saratololo is at minus 30 degrees latitude, and GMRIG is at plus 30 degrees declination. And it's basically, it's above the horizon for an hour one night or something. And then you're looking through more than 2 air masses. So it's not an easy observation. But we've got this very interesting brightening here. GQ Lupi is another star that's sort of in between a really, really active one and a not so active one. It's got these big dips that look like what we saw in RU Lupi. It's got a thing up here that looks very much like that GMRIG brightening. I think that's due to accretion. You have an accretion flow going on for a couple of days, brightening the whole star, and then it fades away. And you've got a flare. This is a magnetic flare. It's very short. It goes up very fast. Fast rise, exponential decay. And we see flares like that on the side. Not this big. This is a flare where the star brightens by 20%. That's a big flare, but it's very fast. It's not an accretion event. As the disks dissipate, as the stars sort of wind down, a lot of the accreted matter goes into planets or goes into the star itself or gets blown away. Eventually, you end up with no disk. And then you see the stellar photosphere. And what you see in a star like this is GW Orionis. There's a flare here. And there's no real trend. But it's more or less periodic. These are probably star spots. And we can probably tell if we have the spectrum. Now here's a star that's clearly spotted. This is a G5 star. It's a little bit more massive than T Tauri. It's 1 million years old. It's in Taurus. It's about 9th magnitude. It's a fairly bright star. And it rotates in a couple of days. And it's a very nice sinusoidal modulation. This is a spotted star rotating. And there may be some flares in there, but they're hard to see. Another one that does show flares, this is in the Orion star forming region. It rotates a little bit more slowly. It's 2.5 days or so. There's some flares. There's a nice flare here, a little one here. So these are stars that are sort of like the sun on steroids. They don't have the chaotic variability because they don't have that disk. These are diskless or naked T Tauri stars. But they're rotating a lot faster than the sun. They have strong magnetic fields because the magnetic field is driven by the dynamo, which depends on how fast the star is rotating. So there is a lot of star spots because there's a lot of magnetic flux coming up through the surface, and a lot of energy can be dissipated when they flare. These are 3 stars like that in Corona Australis. They rotate in periods between 2 and 4 days, and you can see some very nice flares in them. But if you ignore the flares, they're just sinusoidal modulators, up and down, spots on one side of the star. Probably spots everywhere, but there's more on one side of the star than the other. So we're just seeing stars rotate at this point. And this is what these flares look like up close. This is test photometry. This is not something that's easy to do from the ground. These are data points every 30 minutes, 30-minute integrations. On the right, here a pre-main sequence 3 has 2 flares overlapping. But we're talking about time scales of a couple of hours. And it's hard to do this from the ground. one thing, you have to be lucky. It's got to happen during the 8 hours or so that the star is up and you can observe it. So this is a summary slide, basically, of what's going on in the evolution of T-Tauri stars and what's causing their variability. We start off with the big disk secreting, it's forming planets. We're looking either from just over the top of the disk in T-Cha or from face down in the case of TW Hydri, and we're seeing these magnetic loops here in red. That's where the accretion occurs. And over time, that disk dissipates because it collapses in towards the midplane. The dense stuff near the midplane may be, well, certainly forms planetesimals, may eventually form planets. You still have accretion going on. This is a star, perhaps like GW Hydri or GW Orionis. And eventually you start evaporating all of the gas, the dust has all gone into bigger things. Planetesimals self-shielding, so the dust, so the gas is illuminated directly by the star and it gets blown away. And this is the case of the naked T-Tauri stars. There's basically no inner disk left. And then you end up with planets. Or in this case, a zoo of planetesimals. And at that point, I've lost interest because they're really not varying much anymore. They're just young stars. Actually, they're still interesting, but I have my hands full with the T-Tauri stars. So back to T-Tauri. You saw this slide, wildly variable, much in the mold of T-Cha, up until 1917, and then it stopped. Why? T-Tauri is a binary star, two young stars. T-Tauri itself is observed more or less face on. It's not being observed through its own disk. It doesn't have much of a disk. It's almost a diskless system. But down to the south here is T-Tauri South, which is actually its own binary. And T-Tauri South, even though it's more massive and more luminous than T-Tauri North, is invisible in the optical. It's observed edge-on through its disk, much like Gomez's hamburger. This is an image of the star system in the ultraviolet. This is the light of molecular hydrogen. And T-Tauri itself is the bright point right here. You can see it. T-Tauri South is located about here, right in the middle of that dark bar, obscuring bar. So we can see T-Tauri North, we can't see T-Tauri South. It's a binary, it's in orbit. And we have some idea of how it's moving. This is a paper by Schaefer, 2020. We have a few points along the orbit. It could be an orbit that takes 5,000 years to go around, or it could take 500 years. It's hard to tell. There isn't much of a baseline here, but but we know how it's moving, and it's moving in the sense that that relative to T-Tauri, the bar, what used to be up here, and now it's down here. So a century ago, probably pushing back a few centuries before that, we were observing T-Tauri North through the disk surrounding T-Tauri South. And it's not a uniform brick that you're looking through, but so you see it being highly variable. It's not terribly variable now, but as the orbit proceeds, it'll come back, and in a few hundred years, T-Tauri may become wildly variable one more time. So that's my story about T-Tauri stars. The takeaways are that all stars are variable. Some are more variable than others. And if you have a satellite like TESS with high fidelity, because you're above the atmosphere and high cadence, you can see everything varying. The variability in T-Tauri stars has many causes, some extrinsic and some intrinsic, and it takes a lot of effort to try to separate them. You can't just do it from the photometry. And we can see these stars evolve as their disks dissipate, the variability amplitude goes down, the chaotic amplitude goes down, modulations become more regular because the star starts dominating the spots on the star, and flares become more evident because these small magnetic flares become stronger relative to the chaotic variability due to the obscuration. So that's my story, and I'm sticking to it. I will take questions.
Well, how much mass are you talking about? How many Earth mass is being sucked in?
Oh, not much, not many. The mass accretion rates are of order 10 to the minus 10 to 10 to the minus 6, probably not that high, solar masses per year. At 10 to the minus 6 solar masses per year, these are the most extreme ones and the youngest ones. In a million years, you build up a whole sun. At 10 to the minus 8 solar masses, you're doing it for 10 to the for a million years, you're talking about a couple 1% of a solar mass, which is 10 to the 4th solar mass, Earth masses. So it's big on a planetary scale, but very small on a
Like
stellar scale.
Jupiter being sucked in?
Yeah, we can observe what the mass accretion rate is in of order 10 to the minus 8 solar masses per year, typically.
Can I just say, if anybody on Zoom has a question, you can either put it in the chat or just shout out, whatever. Because if, we'll take questions from Zoom as well.
So we actually, my wife and I visited that telescope here at Tololo. And there's part of the sky it can't see because of the dome of the 4 meter.
Yes.
Did it ever become an issue for you wanting to look at a star that was there?
No, because I'm usually working towards the south. Yeah, there is part of the sky that's off limits. It's to the northwest, and it's below. No, it's further north than plus 30, like at plus 40 or something. It's not a part of the sky you'd normally be observing anyways.
Can I ask a crazy question? Remember a few years ago, there was all in the news about this star that was dimming and very variable, but in an erratic way. And people were saying there were alien spaceships surrounding
Yes,
it. I mean,
Tabby's star.
Yeah, what was any update on that?
I think it stopped burning.
Okay, but how does that compare to, like how does that relate to the stars you're discussing tonight? Just completely different? Or?
Well, not really. I think the amplitude of the variations are less than what I showed you here, but time scales are comparable. I don't think anybody's figured out exactly what it is. But it's probably obscuration by circumstellar material, much like a Tauri star.
I have a question for you.
Yes.
How do you see the James Webb Space Telescope, being able to help here? And will it be 5 years before you get on it, or what's the time frame for opportunity, and is there opportunity to help with what you're doing?
The James Webb will be very powerful for studying the inner disk. Because the inner disk is 1,500 degrees down, and so it emits in the infrared. It has very good spatial resolution. You may be able to spatially resolve some of these inner disks too. But it does infrared spectroscopy. I have not thought about using it. I've got my hands full right now.
Okay.
But I guarantee you, there are some Tauri stars in the observing plan for the first year.
So there was a paper in Science a couple of years ago, I think it was Science, that argued that the sun is abnormally quiescent. That it has much less variability than most
Mhm.
And that lack of variability is one of the reasons why life could evolve on the Earth. It wasn't subject to the kind of flares and UV blanketing and other good stuff. But you showed us the sun still has some variability. So the question is does that argument make sense? And are there other stars like that that are hypovariable?
The sun is not a very active star. There are stars that are older and less active. I don't think the sun is particularly abnormal. A lot of bias is involved in claims like that. As far as activity and life and things like that, it's the atmosphere that protects us. And the magnetic field protects us from coronal mass ejections, and the upper atmosphere absorbs ultraviolet light. And for the first 4 billion years, there was no life on land. It was all underwater, and water is a great shield against ultraviolet light. So I don't think you can use arguments about activity to say whether or not life gets going.
Okay, thank you. Let's see.